Okay, so we're talking about resonance now.
Okay.
Resonance is essentially the electrons that are moving around, and so the bond can move from one bond to another. The electrons can move from one atom to another, but this is now getting to the point where the the atoms can hold charges and whatnot. So first thing I need you to do, let's see if you remember what carbonate is.
CO3.
CO3, very good. CO3.
Oh.
What's the charge?
-2.
-2, that's right. All
Oh
right,
wow, this is top of my head. I'm pretty good.
pretty awesome. All right, so what's going to go in the middle here? The carbon or the oxygen?
Carbon.
Carbon. And that means the oxygens are going to go around it, right?
Yeah.
All right, so we have one carbon and we have three oxygens. So how many valence electrons does carbon have?
4.
4. So we have 1 times 4. How about oxygen?
6.
So it's 3 times 6. All right, so we got that from saying 1, 2, 3, 4, 5, 6, 7, 8, in case you're a little confused. Okay, so when we add these together, what do we have?
22.
22 electrons. The problem is we have a -2 up here. So are we adding electrons or are we subtracting them?
Subtracting.
Try again.
Adding.
24 electrons. Because remember,
Okay, that's like,
electrons are negative. So
yeah.
since they're negative and it's a negative charge, we're getting more electrons. All right, so how many electrons do we have in these bonds?
2.
2 in each of them, right? So how many
Yeah.
do we have total?
6.
So 24 minus 6, how many do we have left over?
18.
18, very good. All right, so that means we need to put them around here. So we have 2, 4, 6. So we have 2, 4, 6, 12, 14, 16, 18. All right, so do you see an issue with that yet?
Yes.
What are the issues you can see? I can actually see like 2 or 3 off the top of my head.
Um, hmm. Hold on, Dr. Tom, give me a second. Um, I don't think you can do math.
What?
I mean, aren't you supposed to have? Hold on, hold on. I don't want to sound stupid in front of everybody. Give me a second. Um,
What's the first thing that's upsetting you visually?
you didn't finish the dots for O, the last O.
Oh, did I not put enough? 2, 4, 6,
Oh.
8, 10, 12, 14. Okay, so let's put a couple more there. All right.
Oh, okay.
Okay, so there you go. Do you see any other issues?
That's still not enough, Dr. Tom. You need 2 more.
2, 4, 6, 8, 10, 12, 14, 16. What's wrong with me, dude? Maybe I shouldn't like. Okay.
Okay.
Are we good now?
Yes.
All right. There's still yet another problem.
Um,
What rule are the atoms trying to follow? What do they all want to be like?
the noble gases.
Noble gases. How many electrons do they want to have around them?
8.
8. That's right. So does carbon or does oxygen here have 8?
Yes.
Does this oxygen have 8?
Yes.
Does this oxygen have 8?
Yes.
So they're all good. They're all happy little clams, right?
Yeah.
What about carbon in the middle?
No, it only has 6.
That only has 6. So we're going to have to share those electrons. So that means that we're doing this, these two electrons here are going to have to end up forming a bond.
Okay.
To make that, and that's where that double bond is coming from. Okay, so I'm going to redraw this, and I'm going to redraw it the right way.
Poor Kaylin is probably confused right now.
Probably. But you just like badmouthed her, so you know.
Did I? Yeah, I did.
Yeah, you did. Auction, 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 and then we're going to have a double bond there from those from that lone pair. And everyone else here is going to have, and so he only has 4 electrons there rather than 6. All right, so out of curiosity, was there anything stopping me from making this one have the double bond up here?
No.
No, so I can actually rewrite this.
Okay.
And make it so the double bond's on top now.
I should definitely get extra credit for being, the only one. You know what I'm saying? Extra credit.
Good to want things. Okay.
Yeah.
So the one on the left got a double bond. The one on the top got the double bond. How about the one on the right? Is it possible for it to have the double bond instead?
Yeah.
Yeah, so we're going to rewrite it again. Notice I had to rewrite it 3 times to get it all straightened out, right?
Yeah.
That's because there's 3 resonance structures. Resonance basically means that the electrons are moving around and it's going from one area to another, and it's kind of more like being shared.
Okay.
And I think Christian's about to join us. Okay, so
Tell Christian he could just put in the chat.
yeah. All right, so there's 3 different places where those bonds can go. What really ends up happening here is instead of having it's here, or it's here, and ends up getting shared amongst them. And so instead of having a 2 single bond and a double bond, what it ends up looking like is the carbon's in the middle and the oxygens are on the outside. And it ends up that this electron is being shared between them. So there's not a definite double bond there.
So it's just 2 more dots?
Yeah.
Okay. Hey, Christian, can you hear me?
Is he in yet?
Hi.
Yeah, I said you're late.
I know, I had an important meeting.
I'm getting extra credit because I was the only one who's online, and you're not getting any extra credit because you're late.
Christian, let me know if you believe that.
I don't believe that.
Yeah, it's true. Funny, Dr. Chavi.
All right. So right now, Christian, we're talking about resonance structures because that's something that we haven't talked about yet.
Okay.
So this is just one of those things that you're just going to take notes with. We had another video before this that was about the actual assignment, and we did the first couple with the assignment. And once the video gets rendered, I'm going to post it in Google Classroom so that way everyone can watch it if they want to. But it was about Lewis dot structure, so it shouldn't be that bad.
Yeah.
Okay. So first thing we need to do is figure out what nitrate is. What's nitrate?
NO3.
NO3. What was the charge of nitrate?
-2.
Try again. Not -2.
Is it -2?
No.
-1.
Is it -1?
-1. All right. So first thing we need to do is just draw a basic Lewis dot structure here. So what is the valence electrons for nitrogen?
5.
It is 5. Right here. So there's 5 valence electrons. We have 1 times 5. We have 5 electrons coming from nitrogen. How about oxygen?
6. I'm hungry.
So we have 3 oxygens, all having 6 electrons. So how many valence electrons are there?
18.
What's 18 plus 5?
23.
23. Remember what I said about a radical? What's a radical?
I don't know.
Maria, you're the one who was listening to it.
Oh, you said, oh no, that part. I think I was, okay, give me a second.
A radical is a single electron.
Oh.
You know how they like to be paired up? They don't like to be by themselves if they can help it. If they are by themselves, it's called a radical, and it means that they react really, really easily, and they're very unstable. All right.
Okay.
So there's 23 electrons here. What's
But
the
you asked
charge
the one.
of nitrate?
-1, so it's 24.
-1. So what happens to that 23?
It gets added into 24. Like 1 added into 24, yeah.
That is why nitrate has an extra electron there, because it doesn't want to be 23. It wants to be 24 because it wants to be an even number.
Wait, where's that electron come from?
That was a word that's actually in this chapter. So as you start doing the reading guide, you'll see that word come up. This is just like a little intro to it. This is basically an intro to the rest of this chapter. Okay, so when we're looking at nitrate, NO3, which one is the least electronegative? Nitrogen or oxygen? Which is further away from fluorine? Is nitrogen further away, or is oxygen further away from fluorine?
Nitrogen.
Nitrogen. So nitrogen's going to be in the middle. Jamaria, are you eating? Are you ever not eating? Okay, so I have nitrogen in the middle. What's going to happen to the oxygens?
It's gonna go around.
Okay, so I'm going to bond these up. All right, so how many electrons are in each one of those bonds?
2.
2. So 2, 4, 6. I have 6 electrons being used. So how many do I have total?
2. Hold on. No, 18.
So let's go through and put in the lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, you follow me so far?
Uh-huh.
Christian, you still there?
Yeah.
Follow me or not?
So, okay, because I'm trying to also remind myself of the Lewis structures. You do, like, you would do that, and then all the bonds count as 2, and then you go in and fill in the rest around it.
You go from the outside in.
Mm-hmm.
You fill up all the outside first. If it's hydrogen, hydrogen will never have more than one line, and it will never be in the middle.
Okay.
So hydrogen never gets dots. But the other ones you want to fill until they meet the octet, which the octet comes from the noble gases.
Yeah.
Okay, now the idea is that they want to have a full octet. So I'm going to do the same thing I did with Jamaria just a second ago.
What was that?
Oxygen here have a full octet.
Yeah.
How about the one on the top?
Yes.
And the one on the right?
Yeah.
Yay, oxygen is all happy right now. Happy, happy, happy. So let's take a look at the middle one, though. Is nitrogen a full octet?
No, it only has 6.
It only has 6, that's right. So because of that, a set of these electrons are going to come in and make a double bond. And that's where the double bonds are coming from, is the fact that they want everything to have a full octet. You follow me with that?
Mm-hmm.
Yeah.
So I'm going to redraw this. You okay, Jabria?
Yeah, I'm just still hungry.
Again, when are you not hungry? All right. So I'm going to redraw this. I'm going to go ahead and give that oxygen, nitrogen, a double bond there. 1, 2, 3, 4, 5, 6. This one only gets 4 dots now. All the other ones get 6, so that way it can maintain its octet. All right, so out of curiosity, did this double bond here have to have that? Did the double bond have to go there, or could I just use the one on the top?
If you use the one on the top.
I could have used the one on the top. It doesn't really matter which one I'm picking. Mm-hmm. So that's where the resonance comes in. So I could have said the double bonds up here. And with the dots around. Or I could have even said that it's on the left-hand side. With a double bond on the left. Those 3 structures are making up the resonance structures. Okay? All 3 of those are considered to be what's called in resonance. And that's usually signified with a double-sided arrow. Meaning that they're flipping back and forth. Okay, so that means that those 3 structures are happening at the same time and the electrons are floating around. We kind of get stuck in the idea that once we draw the electron someplace, it has to stay there. It cannot move. But the reality is, it's moving all the time. It's very fluid. All right, does that make sense?
Yeah.
Christian, you with us?
Yeah, it's not with this one, but if you had, so for the electron, so say if this was NO5, what do you do since there would be 5, technically 10 electrons bonded to that middle one?
Okay, that's an expanded octet, and that can happen. Okay, it's less common, but it's an exception to the rule, and it can happen. Do you have to use the double lines, or can you put the 2 dots instead?
Caitlin said, do you have to use the double lines, or can you put the 2 dots instead?
You literally just read that, Jamaria.
Shut up, Christian. You're late. You don't get any extra credit. Why is it so quiet?
Because I'm typing, I'm sorry.
Okay.
I'm trying to answer the question.
I'm gonna go get more food.
That's a surprise. Okay. So these are just examples of what's happening here. So if I did the Lewis dot structure of this, notice that these 2 are the exact same structure. Okay. We have a double bonded oxygen on the top, on both of them. This is probably the most stable structure. However, because these electrons are fluid, this curved line is saying that the electrons can move, and it's following the flow of the electrons. Notice on the right-hand side, there's extra electrons here. Those 2 electrons came from the double bond. And then we have a negative because it has an extra electron, and a positive because it's losing an electron. How many electrons should oxygen typically have? How many valence electrons?
6.
6. So oxygen is supposed to have 6 valence electrons.
Caitlin wants to know, how do you know when to use a double bond?
Okay. She can't hear us, that's why she doesn't know. To complete the octet.
I don't think that really probably explained it that well.
I know. Carbon and nitrogen only had 6 electrons.
Hey, Dr. Tom, Michaela wants to know if you're gonna get on another week because her computer's not working right now.
I'll probably come back. I'll probably do this once a week.
Okay.
But if she needs to, I can always tutor at any time. She can just get a hold of me.
Okay.
Okay. I'm kind of used to this. Is kind of what I do when I teach online for Purdue. So I'm used to actually interacting in this manner. So it doesn't bother me at all. Does that make sense?
I wish I would have known that on one of those reading guides. One of those hard.
Yeah. You may not have had as much information from those PowerPoints as I thought you did. That's okay. You'll
I
figure
was
it out.
using the book and I kept getting lost.
Oh. Well, then you should have done fine if you had the book. All right. So back to this. If I cut that bond in half and give one electron to oxygen and one electron to carbon, how many electrons does oxygen have?
Wait, repeat.
Okay, I have 2 electrons here for that lone pair. You follow me?
Yeah.
2 here, 2 here. So how many electrons are there?
6.
6.
6. So these are 6 electrons. If I take this bond and give one of the electrons to oxygen and one to carbon, that means I'm giving oxygen another electron from that bond. How many electrons does it have total now?
7.
7. How many valence electrons is it supposed to have?
8.
8.
Not the octet rule. Just looking on the periodic table, how many
6.
does it typically have?
Wait.
Carbon?
Oh.
Oxygen.
Oh, 6.
Oh. Yeah, 6.
6. Okay, so oxygen has 6 valence electrons, according to the periodic table. But here it has 7 in the bonding. So it has an extra electron, right? Because of that extra electron, that's where that negative comes from. I can do the same thing with the carbon underneath here. If I say each bond, that carbon gets 1 electron, how many electrons does it have?
4.
How many bonds does it have?
6. I mean 3.
It has 3 bonds.
I have 6
It
electrons.
has 3 electrons, right?
No, 6.
I'm giving 1 electron to one carbon, 1 electron to the other carbon. I'm splitting this bond up.
Oh, okay.
Okay?
Yeah.
All right. So when I'm looking at this, so I'm giving one this way, and I'm giving the other one to the carbon in the middle. So that means it has 3 electrons from those bonds. How many valence electrons is carbon supposed to have?
4.
4. So carbon has 4 valence. All right, so 4 valence electrons, but it only has 3 there. It's missing an electron. You follow that?
Yeah.
That's why it has a positive charge. These are called formal charges.
I don't like them.
Well, regardless of your desire for them, they still exist. I was about to say something mean, but I stopped myself because I'm like,
Go ahead and do it. No, it's okay. Don't be shy. Put some more.
All right, so we have formal charges there. Formal charges, if we look at each individual atom and say, how many do they have? How many did they have before this all started? When we're doing resonance and when we do Lewis dot structures, we're trying to minimize that formal charge. So that's one thing we didn't discuss last year. We kind of ran out of time, and it was Chem 1, not Chem 2. So this is going into Chem 2 level of difficulty. If I do the same thing over here with this oxygen, let me change the color. So that way it makes it a little bit more evident. Erase all that. If I did the same thing with this oxygen over here, how many electrons are coming from the lone pair?
2.
2 from each of them, right?
Yeah, okay.
How many types of lone pairs do we have?
Um, okay, these squiggly lines are starting to confuse me. Where are we?
Go to the upper left-hand corner.
Okay. Um,
I have 4 electrons from the lone pairs.
yeah.
Okay. So we have 2 here and 2 here. All right. Now, how many bonds does it have?
2.
It has a double bond, so that's 2 bonds. So what's they get 1 dot or 1 electron from each one of those bonds when we're doing the formal charges. So how many electrons are coming from those bonds?
1.
Each.
Oh,
So we have 1 electron each.
yeah.
So we have 2 electrons from that double bond.
Mm-hmm.
Okay. So I'm going to erase that so that way it's a little bit more clear. 2 electrons. All right. How many electrons do we have total surrounding that oxygen?
6.
I have 4 from the lone pair and 2 from the double bonds.
I said 6.
6. I did not hear you say that. I apologize. How
That's
many
fine.
valence electrons is it supposed to have?
6.
6. So 6 minus 6 is?
0.
That's why it's the most stable, because you're minimizing its formal charge. Here it's 0 because it has 6. It brought 6 into the game. It got 6 out of it. Okay? On the right-hand side, it brought 6 in, but then it came out with 7, so it came out with an extra electron. It went from 0 to a -1. So that this one, because it's reducing it, is more stable. However, they can both exist, but this one's going to exist more often. Did I completely lose you two on that?
No, I'm still here.
Christian?
Christian hasn't said anything for like 10 minutes. I'm pretty sure he left.
I don't know. I get it in some parts and not in others.
I'm going to do the exact same process on the bottom here so we can compare it. Okay? So hopefully when we go through it a second time, it'll make a little bit more sense. I should cut that.
What are you cooking for dinner, Dr. Tom?
I'm going to do tacos.
Taco
No.
Tuesday.
What'd you say?
Taco Tuesday.
It didn't even occur to me, to be totally honest. It just seemed like a good idea. Okay, these 2 structures on the left are the same, correct?
Yeah.
All right. I'm going to go through the valence charges again. Okay?
Yep.
These lone pairs. How many electrons are surrounding the oxygen right now with if we just consider the lone pairs?
4.
4.
4 electrons from the lone pairs. Okay, so if I then take these bonds and split them up. So I have 1 electron going to the oxygen and another electron going to the carbon. Okay, so we've taken that and we've basically sliced it in half and say you get this and you get this, like they got divorced. Okay.
Okay.
I know it's morbid.
So
But
then, is it technically considered that oxygen only has 2 around it?
from the bonds or from the lone pairs?
From the lone pairs, you're talking about splitting it up. So is it
The
technically that
lone
there's only?
pairs don't get split up because it's not getting shared with anyone.
Oh.
You only have
The
to
lone
split up the
pairs
ones that
are
are
the
shared.
dots,
Huh?
right? The lone pairs are the dots, right?
Correct.
Okay.
So it has 2 electrons coming from the bonds. 1 from each bond.
Mm-hmm.
So that means I have 6 electrons surrounding the oxygen. Okay?
Oh,
How
okay.
many valence electrons is it supposed to have? How many did I bring into it?
6.
So 6 minus 6 is 0.
Mm-hmm.
That's where we got that 0 from. Let's go over to the right-hand side and do the exact same process. Look at the lone pairs. How many electrons are coming in from the lone pairs?
2. 4, sorry.
4 total, 2 each. 4 electrons from the lone pairs. They are not being shared, so therefore oxygen gets both of them. Okay?
Yeah.
This bond here gets divorced. We're going to draw a line through it. And one oxygen gets half and the carbon gets half. So that means that one of these electrons get pushed towards the oxygen. Can you follow me?
Yep.
Only had one line this time. So how many electrons did it come from the bond?
1.
1.
Electron from the bond. So when you're looking at formal charges, for every lone pair, you get 2 electrons. For every line, you get 1. Okay?
Yep.
So oxygen now has 5 electrons around it. How many did it come into this with?
6.
6. So it had 6 electrons and only has 5 now. So it has less electrons than it started with. So what charge would it be?
Positive.
Positive 1. That's where that positive came from. Okay,
Oh,
that's the
so all this was just to describe why it's positive and which side's negative?
Yes.
Oh, okay.
And that's called the formal charge. And the formal charge is used to find the most stable electron configuration, or most stable Lewis dot structure. Okay, so think of it this way. First of all, you want to minimize that formal charge. So you want them to be 0 if you can. If you can't help it from being 0, you have to figure out what else it could possibly be. Like when I'm looking at this, and I'm looking at a periodic table. Here's carbon, here's oxygen. What's closer to fluorine?
I don't see the periodic table. Oh, oxygen.
Oxygen is closer to fluorine, yes? So if oxygen is closer to fluorine, what does that mean about electronegativity?
It's
Really high.
weaker.
It's really high. So
Dang it.
that means oxygen wants electrons, right?
Yeah.
Mm-hmm.
So does it want to be positive?
No.
No.
No. So what is the likelihood of this happening?
Unlikely.
Very unlikely. It can happen. It's not that it's not going to happen. It's just not going to happen very often. It took us a while to get there, but did you get it?
Yes.
How about you, Jamaria?
Yeah. Yeah. Is this on the worksheet?
It's on the worksheet in a couple weeks. So it's not this week.
Okay.
We have a preview.
Yeah, it's fine. Okay, I just wanted to make sure.
Wait, is this worksheet the only thing we're doing this week?
There's a simulation online.
And then that's it for this week? It's just this and the simulation? Oh, I thought that was only for today.
I'm trying to do 2 assignments per week.
Okay.
Because they said that the assignments had to be about a half hour a piece, and my assignments take longer than a half hour.
Heck yeah, they do.
Yeah, what he said.
Cry me a river. All right. So another thing that they want to say about Lewis dot structures is when it comes to resonance, this is not a resonance. Okay, this is not a resonance because this one is in the middle, yes? Then atoms can't change places. They kind of get stuck in their position and you move around the electrons. You don't move around the atoms themselves. Okay? You see the difference between these two?
Uh-huh.
That's all you have to do with that one. That's why when we were doing the ones where I led you through it, once I got that structure there, I kept it there. I didn't move around the bonds. I didn't put oxygen in the middle suddenly. It still had the same structure. I just moved the bonds around. That's because once those get in that position, they can't move. Otherwise, that's considered more of a reaction than a resonance. Okay, so the other thing I talked about before was resonance was with formal charges. We tried to minimize the amount of formal charges. Let's take a look at these two pictures. What's different about these two from the left to the right?
Well, the double bonds.
Okay, this one has, the right one has double bonds. But
Yeah.
as Christian said, look at the one on the right. Is that a full octet for sulfur?
No, it's more.
It's more. It's called an expanded octet.
I was looking at the wrong side.
Yes, Christian, the L on your hand makes a
I don't know why, but I looked at the left side and I was like, what?
Okay. So this one has an expanded octet. All right, so in theory, it doesn't want to do that. But look at the charges. Look at the differences in the charges. Which one has the least amount of formal charges?
The one on the right.
You're correct.
Oh, okay.
I was writing, I apologize. So that side has the least amount of formal charges, which means that's good. Okay, we try to minimize those formal charges. Here we have a -1, a -1, a -1, and then we have a +2. By throwing in some double bonds, even though it's an expanded octet, it makes it more stable because there's fewer charges. That makes sense?
Yes.
Christian?
Yeah.
Okay, that is the last that I was going to explain with the resonance. I wanted you to be aware of it. I wanted you to realize how the double bonds were formed because they needed to be a octet. And I wanted you to be aware that the resonance is the positive and the negative movement around. And you also learned about formal charges. So everything kind of gets covered. This is actually, this information will take you to the end of the chapter.
Okay.
I am not intending, okay, I'm going to actually stop recording at this point. Unless you guys have a question specifically about this.
Nope. Wait. I want to say something before it ends.
Okay, go ahead.
It
better not be about extra credit.
Huh?
It better not be about extra credit.
It wasn't going to be. It was just going to be, I was just going to actually tell you that nobody is probably going to watch the full thing. But if they do, never mind, just end it.
What are you going to just say it?
No, just hurry up and end it.